At Eaton's Power Systems Experience Centers, we don't just talk about distributed energy, we live it. Our facilities showcase how modern energy sources work together to take power systems to the next level. In the past, we've installed solar panels on the rooftop and parking lot canopy, a vertical windmill, a microgrid with a natural gas generator and lithium batteries, and we even have a microgrid with vehicle-to-grid capability and a Tesla battery pack with solar input in our residential area. While these systems provide backup or supplemental power, we recently added a new technology that offers something different: continuous clean energy, a Bloom Energy fuel cell to provide 50 kilowatts of power all day, every day. So when the sun isn't shining and the wind isn't blowing and the batteries aren't charged, we can still reduce our demand from the utility by 50 kilowatts with a very clean, reliable source of energy. In addition, this unit can also work in conjunction with our microgrid, or with downstream loads, we can use it as an islanded source of power. Prior to the installation, we didn't have much experience with fuel cells, but now that we have the Bloom unit here, we're really excited to share what we learned and how this new technology can take power systems to the next level. First, let's start with this. What exactly is a fuel cell and how does it work? Let's focus on the 50 kilowatt unit we have here. In this unit, we bring in natural gas as the source of energy to make electricity. However, you may think it burns the natural gas like you would with a combustion process in a gas generator, but actually the natural gas is used in a chemical reaction which yields electricity. With a very simplistic explanation, it brings in natural gas, takes out everything that isn't useful for the process, and breaks it into hydrogen and carbon. Next, it combines hydrogen with air, mostly oxygen, in a chemical reaction, again, not combustion. The output of this reaction is water vapor, carbon dioxide, and electrons, or DC electricity. It's considered one of the cleanest energy sources available in the market. And with carbon capture, it can capture 95% of the pure carbon dioxide stream and can be used for food-grade utilization or sequestration. Once the DC voltage is produced, it's regulated and supercapacitors are used to stabilize the voltage. Then it's inverted to AC to put power back onto the electrical distribution system. If it's operating independent of the utility, it sends the power directly to the loads. If it's operating in parallel with the utility, it can send power to the loads and the interconnected distribution system. In the event of a utility outage, the supercapacitors are used to quickly respond to significant load changes and support islanding of the fuel cell. The supercaps in this unit can support about 100 kilowatts for about 30 seconds. Like a solar-powered inverter, the unit we have is grid-tied, meaning that it will follow and run in parallel with the utility system. But if the utility goes out, it can switch into grid-forming mode where it can island, feeding downstream loads. The supercapacitors help smooth that transition to and from the utility. If it's not set for islanded operation, the fuel cell inverter will remain off until the utility comes back and stabilizes. In this mode, per UL 1741 standards, the inverter must detect stable utility voltage for 5 minutes before reconnecting to the grid. For our unit here at the PSEC, here are the main components from right to left. First is the fuel processing module, which is the entryway for fuel. It filters out impurities and distributes fuel to the power modules. Next is the alternating current inverter. Its job is to convert the DC to AC power. In the middle are the power module and a spare space for a replacement unit used for a swap later. This power module houses the solid oxide fuel cells and generates DC power. Next is the step load section. This houses the ultracapacitors, or supercaps, used to provide the step load support in islanding mode. Finally, on the far left is the water distribution module. It provides water for startup and maintenance. From a component standpoint, think of fuel cells as being analogous with solar panels. Let's compare two large systems of each and see how this works. An individual solar panel is like a fuel cell at the component level. A panel may produce 500 watts, and a fuel cell stack might produce 1,000 watts. Next, for solar panels, we put them in series strings to give us a higher output DC voltage, and put the strings in parallel to yield a higher output power. These strings are then connected to a string inverter with a rating appropriate for the number of series and parallel modules called an array. Arrays are then connected to a common system to make up a solar farm and can be hundreds of megawatts. With fuel cells, we start with a 1 kilowatt stack of the individual fuel cell components. Then we combine the stacks into 65 kilowatt power modules. Next, we connect several modules in parallel, and for example, 5 of them, or 325 kilowatts, may be connected to one inverter. These modules plus the inverter are called an energy server. Multiple 325 kilowatt energy servers together like this make a server farm and can be several megawatts or several hundred megawatts. Fuel cells take time to come up to full heat for operational modes, and this can take 12 to 48 hours. So planning the initial startup, commissioning, and operation is critical. But once they're operating, they're intended to stay on for years. In our case, during commissioning, we ran the unit up to full heat, then tested it with the full 50 kilowatt output power. Next, we tested all of the operating cases, including islanding, and then finalized the commissioning, and the unit has been running ever since. So if you wanted to install a fuel cell at your site, what would you want to think about? Here are a few initial considerations. Start with sizing. A feasibility study will help you determine if a standalone fuel cell or one integrated with other DERs into a microgrid is appropriate. This will help you determine the cost-benefit of the installation. For example, if you can offset peak demands during the day when electricity is expensive, you can size based on this parameter. If you're looking for resilience and backup power with islanding capabilities, consider which loads are most critical and size based on that. Other considerations may lead you to size the system based on site-specific goals. Fuel source is another key factor. Hydrogen storage is often the primary consideration of whether or not you store and use hydrogen directly versus deriving the hydrogen from another source like natural gas or biofuel. In our case, we had the natural gas source readily available and hydrogen storage wasn't a viable option, so we used natural gas. One interesting thing we learned about was the pressure associated with the natural gas at our facility. We learned that the fuel cell needed 15 psi of pressure for the natural gas, but our building gas pressure was only about a half a psi. We also learned that our homes use about a quarter to a half a psi, which was surprising to all of us. With this in mind, we reconfigured our building at a higher psi to match the needs of the fuel cell, and then dropped the pressure with regulators for the other gas requirements of our building, including water heaters and HVAC equipment. Here's a drawing showing how our building is now fed to achieve the required 15 psi for the fuel cell. The interesting thing was the gas regulators stepping down the pressure are analogous to transformers stepping down voltage. In some cases, multiple regulators are required and placed in series to achieve this desired level. This is like stepping the voltage down from 34.5 kV to 480 with one transformer and then down to 120 with another. Bloom was very helpful working with us and the gas company since this was not something we're often involved with. The fuel cell requires a water source, especially for the startup, and since we're located in Pittsburgh, we also needed to add heat tracing to make sure the water source doesn't freeze in the winter. Once the system is up and running, it actually requires very little water as it produces a self-sustaining water supply within the fuel cell system. Other considerations include control, monitoring, and operational modes. With this DER, like any other, your control and monitoring capabilities and operational considerations are very important. Again, it goes back to whether you intend to simply provide a fixed kilowatt source all day, every day, or if you intend to change the loading or operate independently from the grid. All of these cases actually dictate the type of control that you'll need. Monitoring and verification of operation are important to confirm that the source is providing the expected output. Bloom offers on-site monitoring and works with the end user to ensure the proper operation and maintenance of the fuel cell and associated equipment. As far as the operational modes, again, fuel cells prefer to operate with a constant load, and initial startup could take up to 48 hours, so ideally, once the unit is running, it's best to leave it on with a constant load. Permitting and interconnection paperwork can take longer than expected. At our site, coordinating with both the electric utility and gas provider was more complex because we now have multiple DERs, including solar, wind, battery storage, and the Energy Aware UPS. If you're installing a fuel cell alone, the process may be simpler, but it's important to plan ahead. So what are the scenarios where you would see a fuel cell? Applications of fuel cells vary from primary power to microgrids to off-grid power. For primary power, the unit provides a fixed level of base load power. This is primarily how we're using the Bloom unit here at the PSEG. With microgrid applications, it acts in parallel and can be used with other DERs and a microgrid controller, or as a standalone unit that separates from the grid and protects critical loads to provide resilience. It can also act as a UPS with loads fed downstream from the unit, with supercaps offering to buffer to protect against fast changes in load or full disruption of the utility power. As a grid-forming source, the fuel cell can run truly independent of the grid. In many cases, optional equipment can add additional benefits like carbon capture and combined heat and power. Carbon capture takes 95% of the pure carbon dioxide stream and captures it for use in food-grade or sequestration applications. For combined heat and power, the exhaust heat from the power modules is used to supplement existing heating and cooling equipment. So why buy a fuel cell versus a more traditional power source? Fuel cells offer unique advantages over traditional power sources. Utilities are generally the lowest cost energy source, but in some areas utility costs can be very high. In addition, resilience and availability are a concern for sensitive loads. As a comparison to natural gas generators, generators burn fuel and are much less efficient. Since they require a rotating machine, they may also require significant maintenance. Solar and wind are good options as part of a microgrid, but aren't always available. Fuel cells don't rely on the sun or the wind. Batteries are great for short demand management in high-cost utility areas, but don't provide long-term outage protection or long-term demand reduction or base load reduction. In addition to these benefits, fuel cells have other advantages over more traditional energy sources. Specifically, considering a natural gas turbine, the ambient temperature, altitude of the installation, and the loading of the unit affect the output power much less on a fuel cell than a generator. So who should consider using a fuel cell? The simple answer is anyone that can justify the payback on energy savings or resilience that's needed to power their facility. Traditionally, they've been favored by hospitals, universities, and commercial buildings in high-cost areas. Today, they're gaining traction in data centers and other large load facilities where utility infrastructure build-out would take years. In these cases, fuel cells offer an alternative energy building block solution that is quick to stand up and is also scalable and reliable. Fuel cells have been around for a number of years, but recently they've taken hold in commercial applications as the cost-benefit of these systems have become an attractive payback for consumers. The Bloom Energy fuel cell has proven to be a great addition to our portfolio of DERs in our Power Systems Experience Centers. If you'd like to see a real fuel cell in action, contact us or your local Eaton representative to schedule a visit to one of our Power Systems Experience Centers today.